Hey guys, this is Mr. Bennett, and this is video number 2 for Unit 14. We're going to continue to talk about gas laws. And the main topic we're going to talk about today is what happens when a variable is held constant. So let's start off with, what does it mean when a variable is held constant? Well, a variable, first of all, might be your first question. What is a variable? Variables are the things, basically the values that can change in our equation. So that would be, for instance, your P for pressure, your V for volume, or your T for temperature. And so what it means for one to be held constant is that essentially it does not change. So for example, when we look at the equation for the combined gas law, we have P1 times V1 divided by T1, so that means the initial pressure times the initial volume divided by the total volume, or divided by the initial temperature, will equal the final pressure times the final volume divided by the final temperature. And so if we were to pick one of these, say for instance pressure, and say that pressure remains constant, then that means whatever the pressure is initially, P1, will equal the final pressure. So it doesn't change at all. So numerically, if we want an example, if we said that P1 was equal to 1 atmosphere, and we said that pressure was being held constant, then we know that P2 will also be equal to 1 atmosphere. So what does that mean in terms of the equation? Well, that means that whatever is held constant, you can ignore. So there are 3 different variables: pressure, volume, and temperature. And that means that we have 3 different ways to hold constant, meaning pressure could be held constant, volume could be held constant, or temperature could be held constant. And what I really want you to understand is whatever variable is constant means ignore it. Okay, meaning essentially it disappears. Okay, so for example, if we're going to hold pressure constant, we know that the original equation is P1 times V1 over T1 equals P2 times V2 over T2. So if the question says pressure is being held constant, that means ignore pressure. Okay, so literally what I want you to do when you get to a question and it says one of the variables is constant is look at your equation, so look at this, and literally put your finger over the variable that's being held constant, so you know, like cover it up, so you know that it's gone, you ignore it. Or write out the equation like this and cross out the one that's being held constant. So what that means is that when you actually go to solve the problem, you don't need to plug everything in, you just need to plug the variables in that are not constant. So in other words, our combined gas law, when pressure is being held constant, changes to look like this: the initial volume over the initial temperature equals the final volume over the final temperature. Because pressure is being held constant, you basically ignore it, you don't have to plug it in. Makes your math problem a little bit easier. Okay, so the same can be said for when volume is being held constant. The equation again is P1 V1 over T1 equals P2 V2 over T2. So if our volume is being held constant, that means volume can be ignored or disappears. And so that means that our new equation becomes P1 over T1 equals P2 over T2. Okay, so we just ignore the volume. So at this point, you should be able to figure out what the final equation should look like. So what I'd like you to do is, right now, you're going to think about what does it mean if temperature is held constant? How will the combined gas law change if temperature is held constant? So pause the video and see if you can determine what the equation is going to look like on your own. Okay, so pause it and try. Alright, so hopefully you paused it and tried. Let's go ahead and do it together. So essentially, if we're holding the temperature constant, the equation is P1 V1 over T1, which equals P2 V2 over T2. And we know that temperature is being held constant, which means that temperature essentially disappears. So we get rid of it. So our new equation is P1 V1 equals P2 V2. Okay, so by paying attention to what's constant, you're able to simplify the equation, make it a little bit easier, which is hopefully going to make your math a little bit easier. So let's do a practice problem together. It says if 21 liters of a gas are held at 3 atmospheres and 150 degrees Kelvin, what will the pressure be if the volume remains constant and the temperature raises to 300 Kelvin? So let's go through and identify these. First of all, 21 liters, that's going to be our V1. 3 atmospheres, atmospheres is a unit of pressure, so that's going to be our P1. And then 150 Kelvin, Kelvin's the temperature, so that's going to be our T1. Now it says what will the pressure be, so that means P2 is going to be our question, that's what we're solving for. If the volume remains constant, that's important, okay? And the temperature raises to 300 Kelvin, so that'll be our T2. Okay, so notice volume remains constant, so if we were to write out our equation, like so, right, then if volume remains constant, that means that we get rid of volume. So this is our new equation, P1 over T1 equals P2 over T2. So I'm going to go ahead and plug in the variables. So again, volume I can ignore, so I don't need to worry about that number. So P1 is going to be 3 atmospheres, 3 atm, over T1, which is 150 Kelvin, which equals, let's see, P2, that's our question mark, right? We don't know that value. And then we know that our temperature is going to change to 300 Kelvin. Okay, so the goal of this is to solve for P2, and this is algebra. So there's a couple different ways we can do this. Now, you could, what people would say is you could cross multiply and divide. Now, that may be easy for you. If you like cross multiplying and dividing, go for it. I'm kind of against it only because it's a two-step process. You have to cross multiply, so you've got to rewrite things over here, and then you have to divide, so you have to write more, and every time you have to write out the equation, that means that there's a chance you're going to write something wrong, meaning you're going to copy something wrong and create an error due to just the way you've copied things or written things. So if you could reduce the number of steps and still be as accurate, that means you have less chances to create an error on your own. So instead of cross multiplying and dividing, what I like to do is I like to multiply by the reciprocal. In other words, I look at the variable over here that I'm solving for, and I can see that we're dividing by 300. Okay, I want to get pressure by itself. So if I'm dividing by 300 to get pressure by itself, I need to do the opposite. So pressure is being divided by 300, so in order to get rid of 300, I need to multiply by 300 Kelvin. Whatever I do on this side, I also have to do on this side. So I'm going to multiply this side by 300 Kelvin as well. So I'm multiplying by the reciprocal, meaning I'm essentially doing the opposite of whatever's happening on that variable side. Okay, these guys are going to cancel out, meaning the 300 Kelvin is going to disappear on this side, so pressure will be by itself. And then on this side, notice my Kelvins cancel out, so they disappear. And then my 300 and my 150, they can reduce. So 300 and 150, 150 goes into 300 twice. So 150 becomes 1, 300 becomes 2. And so I'm left with P2 equals, meaning the final pressure equals 2 times 3, or 6 atmospheres. Okay, so problem was much easier than a simple combined gas law problem because we're able to get rid of the volume. Alright, so what I would like you to do now is I'd like you to take a look at the second problem here, and I'd like you to do it on your own, and then when you get to your whisk, you're going to have a chance to fill it in on your own, or tell me what answer you got. Now once you submit your whisk, make sure that you check the submission page, because the submission page will have the answer, so you can check to see if you were right, and you can look at the other answers to the whisk as well. Alright, so don't forget to do your whisk, and we'll see you tomorrow.